All right. So questions. This is your big chance for PA3, PA4 questions, PA3 questions. We're not on PA4 yet. Yes.
So I know there's a way for like scanf, you can put a phrase at the beginning and then capture a number. So for like star dump, I was trying that, but obviously star is like the, it's a wild card.
No, it's not.
No,
it's just a star.
Oh,
Yep.
so you can just put star dump
Yep.
and then space
Percent D, exactly. Yep.
Okay.
Yeah, scanf is very literal. It doesn't do like regular expressions and stuff like that.
Okay.
So for if-else statements,
Mm-hmm.
you have an if statement, and then you have to immediately have either an else if or an else if.
There is no else if, but you can say else followed by if.
Oh,
But yeah, if you want an else, it comes after the curly bracket, the closing curly bracket.
and it has to be right after that.
You can have space, but yeah.
Okay, because I ran into this issue where I have to print it before, before the else statement.
Yeah, it won't like that.
Okay. I guess it's just how.
Did you want that print to be part of the if, or to
Um,
happen regardless?
well, it was a debugging thing. I just happened to.
Because you could put it inside the if you just wanted it to happen in the if, or you could put it in both the if and the else if you wanted it to happen in both places.
Sure.
Or you could put it after the whole if then else if you just wanted it to happen after.
That's true. But either way, yeah, it was just a debugging thing.
Yeah.
And I just had to use that.
Okay, cool. All right, other questions? All right, on with trees then. So let me draw kind of general picture of a tree. I'm not going to put numbers in here. So the root is always this node on the top. And we talked yesterday about the depth of a node. And you remember what the depth of a node was?
It was the amount of iterations down from.
Yeah, the number of steps we had to follow from the root. So if we start at the root, it's already at the root. This has a depth of 0. This node down here, if we start at the root, we have to go down 1 link. Same thing with this node here on the left. In fact, any nodes I have at this depth are going to have the same depth. Those all have a depth of 1. All right, this node here has a depth of 2, 1, 2. This node also has a depth of 2. So depth is really capturing sort of what layer you're on in the tree, right? If you draw your nodes nicely where they're all lined up and they all go down the same distance, then everything that's on the same horizontal line should have the same depth. So 5, 1, 2, 3, 4, 5 hops to the root. So the height of the tree is just the depth of the deepest node. So in this case, the deepest node we find has a depth of 5, so the height of this tree is 5. So let's think about how we would write a function to calculate the height of a tree. And if you start trying to do this, it gets kind of involved. Because to find the height of a particular node is not hard. You just have to follow the links to the left or the right and keep count of how many links you've gone, right? If I know that from the root I should go right, left, left, I can count up. I went 5 hops and I got to this node. I know that's got a depth of 5. But to find the height of the tree, I need to find the depth of every node in the tree, which means I have to get to every node in the tree. And we don't really have a way to do that yet. I know how to get to the root. That's just the root. That's the start of the tree. And I know I could go to the left and find a node. And once I'm at this node, I know that I can go left or right. Well, I could choose to go left first, and that'll get me to this node. And from here, I can go left or right, so I could try to go left first while there's nothing there. And then I could try to go right, and I find this node. And from here, I could try to go left, nothing there, right, nothing there. Somehow, I've eventually got to get back up here and move over to the right. Right? And once I'm here, I need to come down to the left. And once I'm here, I need to come down and see this node and try to go to the left and the right, and there's nothing there. And then I need to know that I only went one direction on this node. I went to the left. I need to come back here and go to the right. You got to keep track of all of these places that you've been where you made a decision, should I go left or right, and leave a bookmark there to say, hey, when you're done with what you're doing, go back to the last place where you went left and try going right. And there can be a lot of those places, right? Here, I'm going to go to the left. When I come back, I'm going to go to the right. Well, I'm going to go to the left, and then I might have to come back and go to the right. And there's no limit to how many of those we might need to remember. So we can't just have a variable called remember, and when we come here and we say let's go to the left, set this node equal to remember, because you got to remember the other places too. Okay? This actually works really well with a stack. Because not only can a stack remember multiple things, but each time we come down here and we decide to go to the left, that's the place we want to go back to explore to the right. And we want to do that before we come back to the place before that, where we went left and say explore the right. And then we'll come back to the place before that where we said let's go to the left, and we'll go to the right. So a stack works nicely with this, but it's a pain to code. First of all, you have to implement a stack, and then you've got to somehow keep track of each of these places, store that information on the stack so that you can come back and try the other direction, and so on. So let me suggest a totally different approach. The height of the tree is the depth of the deepest node. Agreed? That's the definition. Well, if I have this original tree, remember, I have 2 subtrees. I have a tree sitting over here on the left, and I have a tree sitting over here on the right. The tree on the left, this is the root. The tree on the right, that's the root. What is the height of this tree on the right that we've got boxed in green? What's the deepest node in this tree? It's still this one, right? And how many hops from this node to the root? 1, 2, 3, 4. This tree has a height of 4. Why is that? Because the depth of each of these nodes is 1 less than the depth that it was in the original tree. Which kind of makes sense because the root moved down 1 spot. So this boxed in area over here, the height is equal to 4. This boxed in area over here on the left, the height is equal to 2. Okay, so what does this mean? On the left, I have a node which is 2 hops from this green root, which means it's 3 hops from the original root. Over here on the right, my deepest node, since this is a height of 4, my deepest node is 4 hops from this green root, which means it's 5 hops from the original root. So if I know the height of the left subtree and the right subtree, I can find the height of the original tree. It's going to be 1 more than whichever height is larger. Because the deepest node in this original one is going to be in whichever tree has the greatest height. And however many hops it takes to get from there to this green root, if I add 1, that'll get me to my original root. So I can write a bit of an equation. the height of a tree is equal to 1 plus whatever is larger, the height of the left subtree or the height of the right subtree. And I'm just using tree arrow left to mean the tree at the left subtree. Does that make some sense? It's a recursive definition, so that's always a little disturbing. But logically, right, if I find the height of this and I add 1, that could be the height of the entire tree, unless this left side was even deeper, in which case whatever the height is over here, if I add 1, that's the height of the original tree. So I can write a formula for finding the height of the original tree in terms of finding the height of the left and right subtrees. There's one case in which this formula will not make sense. When would this seg fault? Let's see how good you are at generating seg faults.
One of them is nothing. Or another.
Even more extreme. Yes, you're right.
If there aren't any depths 0, makes sense.
If they have negative X.
So if tree is null, trying to do tree arrow left or tree arrow right is going to seg fault. I'm never even going to call that function. So I'm going to put in a special definition here. The height of the tree is -1 if tree is null. And we mentioned that yesterday, a tree that has nothing in it, we're going to define the height to be -1.
So what's the actual benefit of using this structure?
Because we can write a 2-line height function. And we don't really have to write any code that does anything in that. All right, so keep this in mind. I don't expect this to necessarily make sense. This will alternately be crystal clear, be really annoying, feel like it's cheating, make no sense at all. It'll bounce between these things sometimes, right? If you're new to recursion, these are all, good experiences to go through, because it is all of those things, okay, except that it does work. But it is kind of like cheating, and it is annoying, and it is confusing, and it does seem weird. But logically, it's like tiling the floor with the L-shaped tiles. If I can tile this little floor, I can tile the bigger floor. Right? Well, if I can find the height of these smaller trees, I can find the height of the bigger tree, because it's just one more than the height of the tallest tree. Let's look what this looks like in code. So this is still pseudocode. I'm not going like actual C code on you today, but I want to think about abstract algorithms for trees. So I'm going to pass a root of a tree to this height function, and first thing I'm going to do is say if root is null, return -1. That's our base case. That gets us out of an infinite recursion. Otherwise, I'll say something like integer left equals height of the left subtree. And if root is null, we've already exited. If root is not null, root arrow left is not going to seg fault. Right? If there's nothing on the left of the root, it's just going to be null. And we can call height with a value of null, and height will just return -1. So this is safe as long as root is not null. So I'll set left equal to the height of the left subtree. I'll set right equal to the height of the right subtree. And I want to find which one is larger, so I'll say if left is bigger than right, let's return the left subtree's height +1. Otherwise, return the right subtree's height +1. So there's a height function.
And what if they're
Doesn't matter. We'll return the right's plus 1, which would be the same as the left plus 1. Right? So, how does this work?
I'm guessing, so we're trying to find the height of the actual tree. And I'm guessing we wouldn't know the heights of the left and right trees once you separate them. But I'm guessing what you will know is as you go through that process in the loop, you get to a point where you're comparing only an empty node with another.
Mm-hmm.
And then it just from there it just kind of adds all the way back up.
Yeah, yeah. Recursion is very much this going down a hole deeper and deeper and deeper until sometime you hit this base case and you no longer have to recurse further down, you start coming back up. And on the way up you might start going down again and you'll hit a base case and come back up, and you might start coming down again. And if you were, you know, a rabbit digging a hole, your rabbit would end up looking very much like a tree. In this case, it would look very much like the very tree that you're trying to find the height of. But we're not doing anything with a stack, we're not remembering locations, we're not going back and saying wherever I went left, let's go right now. We're never even doing like count equals count plus 1. Right? The only real math we do in here is we return either left plus 1 or right plus 1. But this absolutely works. So let's do this for a sample tree, and this will probably be confusing as heck. Okay, this is usually not a fruitful exercise to try to understand your code. Okay, but it's a necessary exercise to go through at some point just to sort of convince yourself. Some part of our brain will rebel until we've gone through this a few times and actually seen what the computer is doing when it runs code like this. So let's use this code to find the height of a tree. So let's calculate the height of this tree. So instead of passing a root, I'm going to pass a picture of the tree. And let me number these steps. Okay, so step 1, is the root null? No. Step 2, find the height of the left subtree and save that in the variable left. So left is going to be the height of, what's the left subtree of this tree? It's just this. It's a tree containing a single node, which is a root. Okay, at that point, our CPU pushes the current location onto the stack and it makes a call to this function height with this as an argument. So I'm going to move over horizontally and I'm going to say what happens when we call height of a one node tree. Well, first thing it's going to do is the root null. No, the root exists, so it's not going to do that. So step 2, it's going to set left equal to the height of the left subtree of this node. Well, the left subtree is null, so it's going to find the height of null. And that's going to make another call to the height function. And we're passing it null. The first thing it's going to do is say, is the root null? If it is, it's going to return -1. So left is going to be -1. And then it's going to say right equals the height of the right subtree, which is also null, which will make another call to height, which will look at the root and say it's null. It'll return -1. Right will equal -1. Okay, if left is bigger than right, well, it's not because they're equal, so it's going to return right plus 1. -1 plus 1, it's going to return 0. And this is why I say it doesn't matter if they're equal, because if I did left plus 1, it would still be the same as right plus 1, because they're equal. Okay, so this call to the height function on a single noded tree is going to return a 0. So left is going to be equal to 0. So we've just finished step 2 of our call to find the height of this tree. Okay, step 3 says right equals the height of the right subtree, which looks like this. So it's going to make a call to height. Is the root null? No. Let's find the height of the left subtree. So it's going to say left equals the height of a tree containing just a root. That's the left subtree of this. And all of this is going to happen right here. It's going to call height. It's going to find the height of null, which is minus 1. It'll come back with a minus 1. It'll compare the right subtree, which has also got a height of minus 1. It will add 1. It'll return to 0. So this is going to set left equal to 0. But there's, more calls that happen here. All right, so we've done that. And then right is going to be the height of the right subtree. And the same thing is going to happen. We're going to have some calls over there, and this is going to be equal to 0. And now it's going to say if left is bigger than right. Well, it's not, because they're equal, so it's going to return right plus 1. So it's going to return 1. And so right is going to be equal to 1. So we're in our main call to height again. Okay, root was not null. We called height on the left subtree, got a 0. We called height on the right subtree, got a 1. Now if left is bigger than right, well, it's not. So we're going to return right plus 1. So step 5, return 1 plus 1, which is 2. And that's what we get back from calling height of this tree. Well, what is the height of this tree? It's the depth of either of these, which is 2. So that's the kind of thing that goes on when you have this recursive code, right? But each of these trees that are being called through the height function, right, they're getting smaller and smaller. They have fewer nodes each time. Eventually, one of them is going to be null, and when it's null, we're not going to have to recurse anymore. We're just going to return a value right then. That's the base case getting us out of this.
So, but this wouldn't be viable for like massive trees, because then the recursion would be.
If you have 4 billion nodes and you have a well-balanced tree, it's only 32 levels high. So you'd only go through 32 recursive calls. It's really not a problem. But a lot of things, recursion is not the way to go. But it's not bad for a height function. Yeah,
How did you know the height was 32?
for 4 billion? Because 2 to the 32 is 4 billion. That's why 4 gig drives were a hard limit for so long.
Oh.
Yeah. So powers of 2, 2 to the 10th is about 1,000. 2 to the 20th would be the next, 1,000 squared is 1,000,000. 2 to the 30th is 1 billion.
Okay.
And then go up 2 to the 2 more, that's 4 billion. 2 to the 40th is 1 trillion, but that's why terabyte drives are never actually a terabyte. They're like 900 some gigabytes. Because that idea that 2 to the 10th is 1,000 is approximate, and it gets worse with the bigger values.
So are there certain things that you can only do with recursion, or can you just?
No. I mean, anything you can do with recursion, you can do without recursion, depending on your definitions, right? I mean, you can fake it. You can do recursive calls in non-recursive languages by just using a go-to and keeping track of all of this stuff yourself. But there are some things that are inherently recursive. Although the question of are there useful things that are inherently recursive would be, more of a gray area. But the one that always comes to mind is Ackermann's function.
I thought about trying to write that in the qubits.
Oh, nice.
I tried.
Yeah.
See if it would actually give us more.
There's Ackermann's function, so it takes 2 variables, m and n. And if m is 0, it's just 1 more than n. if n is 0 and m is positive, it's, you know, a of m minus 1, 1, and if they're both positive, then it's that other function. So that's defined recursively. I don't think there's a closed form equation for this. But it's a fun function because, so their example, Ackermann's of 4, 2 has 19,000 digits in its value. This function just grows tremendously. And it's one of the tools that's used to study large numbers, because you start getting into these hyper operations and ways to express things that are more powerful than scientific notation. So Knuth's up arrow notation, for example, which lets you represent, you know, 2 to the 2 to the 2 to the 2 to the 2 a zillion times without writing a zillion of them. There's ways that you can do that. And so this function is just like crazy, and it makes good graphics. And there's an expansion of the recursion. And there's some values, and you have to know Knuth arrows to do those. Recursion is the main way we're going to work with trees. And everything that we do with trees recursively, we could do non-recursively. And we will, in some cases. We'll probably play around with doing some of this stuff by hand using a stack. But practically all implementations of this stuff for trees is done with recursion. On the other hand, there's things that you can do almost more easily without recursion, but get into trouble trying to do it recursively, because recursion can be expensive. But once you get in a recursive mindset, you can kind of go wild, right? Yeah?
Yeah, the thing with recursive functions is that you keep calling the function, it keeps allocating memory.
Mm-hmm.
And it's a certain variable from it.
Yep. Yeah, so every time you make a function call, you have to save not only the return address, but you have to allocate space for local variables. And that's usually done on the stack. Now, the stack's usually pretty big, but if you do 1,000,000 recursive calls, you're probably going to run out of stack space. And then your program just seg faults.
So what uses are a tree compared to a linked list or a hash table? Or
So a tree is going to be really fast to search compared to a linked list, which is order n. And it's going to be log n to insert and delete and search. So it's a nice, efficient all around. If it's a well-behaved tree, which means you have to balance it. All right, so this is an example of recursion. Let me give you another example. I just like doing this. I don't need all of these numbers. So there's a tree, and suppose I want to search for a number in here. Okay, I want to know, is the number 17 in this tree? Is the number 30 in this tree? Okay, and all we have is access to the root. We don't have eyeballs where we can just scan. So we can start at the root. Well, you know, you can go to the left and go to the left and go to the right and, you know, try to hit every node and figure out if your number that you're looking for is in the tree or not, and that's lots of housekeeping and stuff. An easier way and a faster way is if this is a binary search tree, it has a special property, which is everything to the left of a node is smaller than that node, everything to the right is bigger. So, is the number 6 in this tree? Well, start at the root. 6 is smaller than 20, so if 6 is in this tree, it's got to be in the left subtree. We can ignore the right subtree and say, is there a 6 in this tree? Well, look at the root. It's a 10. If there's a 6 in here, it's smaller than 10. It's got to be in the left subtree. So we can just look at this left subtree, which has a 5 and a 4 and a 6. 6 is bigger than the root. So if there's a 6 in this subtree, it's got to be in the right subtree of the root. So now we have a tree with just one node, a root. Is the root equal to 6? Yes, 6 was in our original tree. If we try to do that for a 7, right? It's smaller than 20, it's smaller than 10, it's bigger than 5, it's bigger than 6, so it would have to be in the right subtree of 6, which is null. Null tree can't contain a 7. We can say 7's not in the original tree. So using the fact that it's a binary search tree, we can start at the root and we can travel through the tree and follow links, and comparing the number we want to the value of the node we're on tells us whether we should go left or right. Okay? But that's still too much work. Let's find a really, really lazy way to search a tree for a number. I'm going to say if the root's data is equal to the number, it's in the tree because it's at the root. That's easy. That's a good case. So if I search for a 20, I don't have to do any work. I'll look at the root and say, yeah, 20 is in your tree. Okay, if the root doesn't happen to be the number we're looking for, we're not ready to say it's not in there. We have to search the rest of the tree. Well, here's what we can do. Yeah. I'll search the left subtree for my number. And if it finds it in the left subtree, then it's obviously in the original tree, so I'll return true. If it doesn't find it in the left subtree, I'll search the right subtree. And if it finds it in the right subtree, I'll return true. And if it's not the root and it's not in the left or right subtrees, it can't be in my tree, I'll return false. And there's one problem with this, which is if I pass it an empty tree, and I try to look at the data value or the left or right subtrees of that, I'm going to seg fault. So I need a base case here, which is if root is null. Well, if there's nothing in the tree, then I'm not going to find number in the tree, so I can just immediately return false.
So in general, a tree is memory heavy because of all the recursion?
Not really. Mostly the recursion is limited by the height of the tree, and we try to keep our trees height balanced. Now if we don't, right, if this tree gets to be thousands of levels deep, then yeah, it's pretty memory intensive.
And is there any reason we're only using 2 branches? Could we go like 3?
You can go 3, you can go 4, you can go 26, and we'll play around with some of that too. But 2 is sufficient to be able to do this bifurcation, and it gets us a log base 2 performance. 3 will get us a log base 3. All right, this code works even if it's not a binary search tree, right? Because it's actually searching every node in the tree. We're searching the entire left subtree and we're searching the entire right subtree. It's a little less efficient this way. I could make this more efficient by saying if the root is smaller than the number I want, let's search the right subtree. If the root is bigger than the number I want, let's search the left subtree. This is going to end up searching every single node in the tree. If I make these statements just a slight bit smarter by saying, you know, if the number is to the left, let's search the left subtree, then I'm only doing, you know, 1, 2, 3, 4 checks. And that'll be nice and high performance.
But that's the fastest you can do it in binary.
Log n, yeah. All right, so classic recursion, right? And the only comparison we do is this statement right here. We check to see if the root of a tree is equal to the thing we're looking for. But kind of magically, that ends up searching the entire tree because of these calls down here. So recursion is easier to write usually once you're used to thinking in that mindset. It's arguably slower and inarguably more memory intensive. But, you know, programmers' time is pretty valuable. And if we're talking about the difference between a 1 millisecond runtime and a 2 millisecond runtime, nobody's going to care about that.
But it's
Right.
double.
But it's what?
But it's double.
But it's double, yeah. But, you know, if you're going to do that a billion times, then it might be a significant factor. But not for PA4. Okay, so let's talk about traversing. So let me put a tree back up here. So traversing means it means basically visiting every node in a tree. And you can think of it as, you know, starting at the root and you want to walk through this tree and you want to visit each node along here. Okay? Now typically what we're doing when we traverse is we're printing the value of the data field inside the node. So traversing a tree usually means printing the values of each node. But you can think of it as a walk, right? And you want to visit each node. And there's different ways we can do that. I mean, we can start at the 40 and we can go to the left and visit the 20, and we can go to the left and visit the 10, and there's nothing else to visit down here. We can go back to the last place we made a choice and go to the right instead and visit the 15. And then we're kind of done with this. We can go back to the 40 where we went left, and we can go down here and visit the 60, and we could, you know, piece together some algorithms for visiting all these nodes. There's a number of ways to visit the nodes in a tree or traverse a tree. I want to show you the most common one. And this one is particularly useful because if we have a binary search tree and we traverse the tree in the following way, we will visit our nodes in order. We'll visit the 10, the 15, the 20, the 40, the 50, the 60, 65, 67, and 70 in that order. So there's a variety of ways to do this. The way I want to talk about is called LNR. It's also called in order traversal. And I'll write it as an algorithm. And this algorithm is almost always written recursively. So let me call this LNR, and I'll pass it a root. And let's say what we want to do is print out the value of each node in our tree in ascending order. Okay, we need a base case. If root is null, return. We're always going to need a base case when we write recursive code, because we don't want to just keep endlessly calling the function and have that function call itself again and again, because it'll never finish and it'll blow up the stack. So there's got to be something that gets us out of this. In this case, it's when the root is null. There's nothing to print, so just return. All right, suppose the root is not null. Let's traverse the left subtree. That's a recursive call. Let's print the data in the root node, and then let's traverse the right subtree. That's your whole traversal algorithm. So it's completely recursive. It calls itself twice, and it prints one piece of data in the middle, which is the root. But if you work this through, you'll find that it actually prints the contents of every node in the tree, and it prints it in the right order. So let's just approximate what this is going to do. I want to do an LNR on this tree. Bless you. Okay, first thing it's going to do is the root null? No. Okay, it's going to say let's do LNR on this subtree. Okay, so we're going to make a call and we're going to say let's do LNR traversal on this. So here's step 1, here's step 2. Do an LNR traversal on this. Okay, so what does LNR say? Is the root null? No. Let's do an LNR traversal on the left subtree, which is a 10. Alright, I'm going to pop up another level of the stack. Let's do an LNR traversal on a tree containing just the number 10. Okay, if the root is null, no it's not. Let's do an LNR traversal on the left subtree. So this is going to make a call to LNR of null. And I won't put another piece of paper down for that, because we know if we do LNR on null, it's just going to return. So this LNR on root left is not going to do anything. And then it's going to print the root data, which is a 10. And then it's going to do LNR on the right, which is not going to print anything. Okay, so I'm going to write an area here for what the output is. And it just printed a 10. Okay, that was the result of traversing this tree. Okay, we're done traversing that tree. We were traversing this 2010-15 tree, and we just finished this step which said traverse the left subtree. Now the next step says print the root data, so we're going to print a 20. And now we're going to traverse the right subtree, which is this 15. And we'll make another call that looks like this, where we say let's do an LNR on 15, and it'll find the left is null. It'll print the root data, which is a 15. I didn't have a good tree to start. Let's make that a 25. Alright. So now it's going to traverse the right subtree, which is a 25. It looks like this. It'll try to traverse the left, which is null, doesn't do anything. It prints the root data, which is 25, and then it tries to traverse the right, which is null. It doesn't do anything. We have now finished traversing this tree, LNR. And we return from that call, which was right here. We're back in our original call to traverse this tree with LNR. The root wasn't null, we traversed the left subtree. Now we're going to print the root data, which is a 40. And now we got one step left, which is to traverse all of this using LNR. If you keep doing this, you'll develop habits for doing this without writing everything out on separate sheets of paper. Basically, to traverse this tree, first it's going to traverse the left subtree. Well, if something only has a root, it's just going to print that root value. And then we're going to print the root of this tree, which is a 60. And then we're going to traverse this tree. Well, what's it going to do? It's going to traverse this tree first, which will try traversing the left, which is null, print the root data, and then traverse the right, and traversing a node with just a 67 will print the 67. That completes the traversal of this, which was the left subtree of this. We traverse the left, we print out the root value, and then we traverse the right, which is null. That completes the traversal of this, which was the right subtree of this, which means we've completed the traversal of this, which was the right subtree of our original root, which means we've completed the traversal of the original tree. And our output was all the data in the nodes in order. So that's not a skill you necessarily want to develop or show off in public. But after you do this enough, you develop this skill, right? Where you can do the recursion in your head. Okay? But my suggestion is the first few times you're trying to do this, do it on paper. And if you have like access to sliding boards, these work great. Because every time you make a function call, you can slide over what you were doing and save that on the stack and start your new recursive function there. And if that has to call itself, you can push that over to save it on the stack and make a new call. And when you return from that, you can bring back the last place that you were and continue. Right, so these work really well for that, or just pieces of paper. So LNR traversal is a common way to visit all the nodes in a tree, and it gives us our data in the correct order. And we could do right node left traversal, where basically we traverse the right node first, and then we print the root, and then we traverse the left subtree. And if we do that, it works exactly the same, except we'll get our data in decreasing order. But we can also do something called node left-right, which says first print the root data, then visit the left, then visit the right. And that gives us a totally different order. It would give us a 40, and then a 20, and then a 10, and a 25, and then a 60, and a 50, and a 70, and a 65, and a 67. And it looks all jumbled up, but it's actually meaningful in other contexts. All right, so this has been abstract, right? I'm using root arrow left for the subtree, but I haven't told you what the node structure looks like, but it's like a list structure. It just has another pointer. And I'm avoiding code for today. Tomorrow we'll talk about PA4, which is going to be your database of license plates, but built with a tree instead of a hash. So you'll read in that same file of plates and names, and you'll store that information in a binary search tree, and then the user can type in a license plate, it'll search the tree and give them the matching value, and we'll have some commands for deleting things from the tree or looking at the contents of the tree and stuff like that. So it'll be similar in function to PA3, but no hash, no linked list, it's just going to be a binary search tree. All right, so we'll continue with all of this tomorrow. Finish up your programs and make sure you submit them and make sure I'm a reporter, and we will go from there. All right, I will see you tomorrow.